Okay, so now we are on lesson 17, if I'm not mistaken. Let me see. Yes, we are on lesson work energy here. So we are on lesson 17, correct. So we're going to be doing this question. It's from a previous question paper. I don't really remember which one, but that's not important. So let us read through the question statement quickly, as well as the questions, before we actually get down to solving them. So they say a 70 kg box is initially at rest. If it's at rest, they mean that its initial velocity is 0. At the bottom of a rough, that's another keyword there. Rough means that you can actually see, if you look closely, that incline, that slope of yours is rough, meaning that there is friction. At a rough plane inclined at an angle of 30 degrees to the horizontal. The box is pulled by means of a light inextensible rope held parallel to the plane. So this is a rope and somebody is just pulling at this. And then they say that the force applied to the rope is 700 newtons. So that pulling force on the string is actually going to be about 700 newtons, which we call tension. So let us now continue, and you see that it actually does make that the incline, the slope makes that 30-degree angle with the horizontal. Okay, and then is that it? Okay, so and then they say, what is the name given to the force in the rope? So what is that force in the rope? We know this, it should be its tension. So it's 1 mark. You don't need to over explain yourself. And then they say that give a reason why mechanical energy of the system will not be conserved as the box is pulled up the plane. So the reason, remember, we spoke about the conservation of mechanical energy in the previous lessons, and we said that it is conserved if it is an isolated system, means that there is no presence of external forces such as friction. But now they did mention that our surface is rough, meaning there is friction, so mechanical energy will not be conserved because of the presence of that frictional force. And then these questions are more of calculations. You're gonna do them later on. Let us just read through them. They saying that the box is pulled over a distance of 4 meters. So they're giving you the distance at which the box is displaced. Then they say the kinetic frictional force between the box and the plane is a 178.22 newtons. The first question, which is 4 marks, is you should draw a free body diagram. We've already done lessons on how to draw this, and we will see how this one can be drawn. Calculate the work done by the box on the box by the frictional force over a distance of 4 meters. Okay, it's 3 marks. It's not going to be an extensive calculation. And then use energy principles to calculate the speed of the box after it has moved 4 meters. Okay, and then the box, so remember, speed is just the scalar version of velocity. So velocity is a vector, whereas our speed is a scalar quantity, meaning that you don't need to include direction when we report the answer. And they say when the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide back down to the bottom of the inclined plane. And they're asking us what would the total network done by, not the total work done by friction when the box moves up then down the bottom of the inclined plane. So we're going to do all of this. So another thing that I wanted to mention, but now it seems to have escaped my mind. Let me think. Okay, I think I'll remember it when we're actually doing the actual question. So we have already answered question 5.1 and question 5.2, and now we're just going to start from question 5.3. I hope that you were able to actually jot down the question statement in your answer book. And question 5.3 required us to draw a free body diagram, and we're going to do that very quickly. And there are 2 methods that you can actually use. So let us do it very quickly. Okay, so this would be normally how you draw those free body diagrams. Like I mentioned, there are two ways you can do it. So remember, our object is going up an incline. So we have a box that is on an incline. That's why this thing is not like this. So you don't draw it as a straight line, you draw it as an incline because it makes that angle, which we said was 30 degrees with the horizontal. And then up the slope, there's a force there. We said it's tension that is pulling this thing up the slope, that tension force. And then the force that opposes motion would then be your friction. So it's pulling it down as it's going up. And then a force that is 90 degrees, so that this force is like at 90-degree with the slope. So you see that it makes that 90-degree angle with the slope. We call it the normal. And then another force that is just going down, it that is always going down, is your FG, which is your weight. So if you decide to draw the weight vector as it is, this force, you don't include the components. If you decide to draw the components or the parallel as well as the perpendicular component of the weight, you don't draw this vector fg. So that is always the distinction that you always remember. Otherwise, you'll be penalized for that. So that is always remember that. And we've already done how is it that you actually resolve this weight vector or gravity into its parallel and perpendicular component. And you see here we have our normal, we have our tension, we have our perpendicular component, which is now, if you look at it, it's actually perpendicular to that incline as well, because the angle between it is actually 90 degrees. And then we have the parallel component. So this is your incline, and then it's going in the same direction. The angle between them is 0, as you can see. All right. And now another thing that is important is that you always have to show. So you have to say what Fn is. It's the normal. If you're not going to write it in full in your schematic, Ft is tension, Fg is weight, and all of these things, so that if a person who's marking you should know what all of these things mean, right? And then our next question is going to be, they require us to calculate the net work done. No, I'm like, calculate the work done on the box by the frictional force over a distance or over the displacement of 4 meters. So now remember, so we are at 4.4. 5.4, I'm lying. So our equation for calculating work is this one, equals to F, a change in X, a cos of theta. So in this one, they actually want that frictional forces. So it's the work done by the frictional forces. And they gave us the value of friction, and they say that value was actually, so it's kinetic friction because it's moving. They say it's 178,22 newtons. And now we know, let's just draw this. I'm gonna redraw this. So we have this object that is moving up. So it means that it is moving from the change in displacement from maybe here to a certain distance is going to be 4 meters. And it's moving in that direction. But you also know that friction is pulling in the other direction. So if you look carefully, so we have ourselves friction that is pulling down, it's against motion, and we have our displacement, that our object is being pulled up. So the angle between them, if we treat this as 0 degrees here, and we start at this point at perpendicular to it will be 90, and then all the way here will actually be 90. So the angle here from where the direction of the displacement to these frictional forces, which work we calculating the work for, is actually 180, meaning our theta will actually be a 180 degrees. And then work is a scalar quantity, so you don't need to worry about direction or putting a negative or a positive. I think this marker is just running out. So we'll say work done by the friction will be given by Our frictional force, they said, is 178.22. Our change in X multiplied by 4, the cause of 180. And you can just put this in your calculator and you should find a value of about a negative of 712.88 joules. So you see, we didn't have to put a negative F. This theta already takes care of our direction for us. So the cos of 180 is actually a negative 1. Hence, this answer is negative. And what that means is that 712 88 energy is being taken away from the system because of that frictional force. So now let us move on to question 5.5. And question 5.5 reads as follows. It says that, let me just see, use the energy principles to calculate the speed of the box after it has moved a distance of, let me see, of 4 meters. So I'm going to use about 3 methods that we can use to calculate this. We have about 3 methods that we can use, and I'm going to do all of them because I want this thing to become very clear on when to use a certain equation and when to not use a certain equation. All right. So let us start this conversation over here. So we've already drawn our free body diagram, and let us say the direction of the forces up the slope will be positive, so that it's the direction of motion. So we can always select it as positive, and the direction against motion, let us select it, which is down the slope or down the incline. Let us say it's negative. So to calculate that speed that they require us to calculate, we can use either this equation or this one. I'm going to use both to show you how we can do it. So let us start with this one, this one is called the work energy theorem. You were introduced to this in the previous lesson, and this one is just the work done by non-conservative forces. In this case, our non-conservative forces would be tension as well as friction. So those are the forces that are dependent on the path taken by the object. The others are not dependent on the path, like your normal and gravity. It doesn't really matter if your object is going up or down. That normal and gravity will always be down, and your normal will always be perpendicular to your surface. Okay, so let us do that. So if we use our work energy theorem, and our work energy theorem actually says to us that the total net work done is equals to the change in kinetic energy, which we know we can rewrite it as EK final minus EK initial. Okay, so for this though, we don't actually have a W net. So how do we find it? Our first task is to find W net, and to find W net, we know that W net, or the network done, can actually be found by saying the total network done multiplied by the displacement. I'm calling the displacement a change in X, as well as the cosine of theta. So meaning, to find W net, I first have to find F net. So let us do that. How do we find F net? So because we are only interested in this motion up the slope, your object is not moving up or down in this direction. It's just moving in this way. We'll just simply say our F net. So we say our F net is all those forces acting on that object. So let us see. So in this direction, how many we have? About 3 forces. We have our FG we have the component FG parallel, and we say down the slope is negative. So it's going to be negative FG parallel plus, because remember the net force is just the sum of all the forces. We also have another force here, which is your friction. So we also say that plus that frictional force, but remember it's down the slope, so it's actually negative. So we have negative frictional force. Let me do this quickly. And then our tension is up the slope, that pulling force, so it's going to be positive, what is that? Positive Ft. And then let me just, before actually moving on, calculate the value for FG parallel as well as FG perpendicular so that we can always refer to them later on. Okay, so now we have calculated the value for the perpendicular, the parallel component of weight, and we found it to be around 343 newtons. The perpendicular component, we found it to be 594.09 thing. And remember, this theta, this 30-degree angle that incline makes, we only use it to find this this parallel and perpendicular component only. So please do not confuse that theta with this theta. They are not the same thing. This theta is just the direction between the force at which the force that we are interested in, as well as the direction of motion. This theta here is that angle with that your thingy, your incline makes with the horizontal. So always know that those two differences. So we have found that, and now we have found that our FG parallel, we said it's 300, and so it's going to be negative 343 minus our frictional forces, which was given to us as minus is 178.22, and then plus 700. So if you do that, you put this in your calculator, you should come to a value of about, I think, 178.78. It's positive, meaning it's up the slope. So our net force is actually in the same direction as our motion. Remember, our box is moving up an incline, as well as the net force. They are in the same direction. If they are in the same direction, what does it mean? It means that the angle between them is 0. So we can now substitute this back into this equation, F net, so that we find the total net work done. So W net is going to give us 178.78. The change in X is multiplied by 4, multiplied by the cos. We said that the angle between F net, we found it to be positive, so it's also up the slope, as well as the motion. It's 0, so there's no angle between them. So you can just simply say the cos of 0. And if you put that in your calculator, you are going to come to a value of about 715.12 joules. And this is newtons. So don't forget that. So make sure that you at least you get the same values as this one. So now we are not done. We were looking for W net. We have found it, and now we can substitute it back here so that we can find that speed that we were asked to find. So let's just do that very quickly. I don't want this video to be long. So we have that W net is equals to EK final minus EK initial. So we have the value of W net. We found it to be 715.12. So it's 715.12 joules. And then we know, so the formula for kinetic energy, so we have mv(F) squared minus 1/2 mvi squared. So initial minus final. So they told us that our initial velocity, they said that block was at rest. So meaning our initial velocity was actually 0 meters per second. So if I put 0 meters per second here, it's going to give me 0. So meaning this whole entire thing will just be equals to 0. And then we'll be left with 715.12, which is equals to a half. The mass of that object is 70 VF squared. And now it's just a matter of dividing this side by a half of 70 and then putting it in a square root. And then you're supposed to come to an answer of about, let me check. You're supposed to come to about an answer. You should find your VF to be, so this is just going to be 715. A half of 70 is 35, and you put this entire thing in a square root, you get an answer of about 4.52 meters per second. It's positive, meaning it's going up the slope. Okay, so this is the first method that we can use to find our velocity, no, our speed. So this is actually our speed. I'm lying. If it's speed, you don't need to include direction. You can just say it's 4.52 meters per second because speed is just a scalar quantity. What's another way that we can use? So another method that we can actually use is to calculate, instead of using Fnet, just calculate the work done by all of these forces that we have on our acting on this. So we can say, okay, the total net work done is given by the work done by the tension plus the work done by friction. So the work done by friction plus the work done by the normal plus the work done by the parallel component plus now the work done by the perpendicular component of what is it, of weight. So now we go here. So we say, okay, so the work done is going to be, need a bit more space. Maybe I should have, let me just flip this thing around. Okay, so there we are. I've already added a few more things. So you have work done by tension, friction, normal, a parallel component of weight, perpendicular component of weight. And we know the equation. So the force in question here is the force of tension. We have the value for that. We already calculated the work done by the friction in question, I think 5.3. We found it to be 712.88. The work done by the normal force, then all of these things. So now let us look at this sketch here. So we can agree that here it's 0 degrees. So remember the motion of this, the displacement is also in this direction. So the angle between this thing and this thing, even though I draw it at the bottom, it's just to show that there is displacement. They're actually on the same line, right? So the angle between for tension as well as displacement is 0. So our theta is going to be 0. The work done by the normal force, the angle between the motion of my box as well as the normal, it's 90 degrees. So theta there will be 90. And then for this one, the angle between friction, remember we used 180 because our finger was moving in this way and then our friction is pulling down and the angle between them is 180. For the same thing applies for the parallel component because it's moving down and then our object is moving up the slope, so that angle will be 180 as well. But then the angle between our motion, which is going up, as well as the perpendicular component, so we're moving it from here, that angle is actually 270 degrees. So that is the one thing that I wanted to show you guys. So let me just fill in everything now, all of those angles as well as our displacement. So have a look at it. So here we have cos of 0. We know the value for this. Here we have a cos of 90, the normal. But this is an important thing. Where is the 594 coming from? So remember, in our sketch, this Fn, the normal, is actually equal to the value of the perpendicular component because this thing is not moving up or down, so they are balanced. And we already had calculated the value of the perpendicular component and we found it to be 594.09. So it is because Fn, the value of the normal is equals to the value of that perpendicular component, and then you can just input this in your calculator and you're supposed to come to a value of about, how much is the W net, of about 715.22 joules, which is the same 715.22 joules. So remember when we used this equation, W net equals to F net changing as cos theta, we came around a value of 715.12. This differences here in the decimal numbers is because we rounded off earlier. So if we had not rounded off, these values would be the same, but you can see that they are actually more or less the same. That means we can use either method to calculate the total net work done by the total net work done in that system. And if we now have the total net work done, we can now go back to that equation of our kinetic, so which said W net equals to a change in EK, and then substitute it, and then you'll find the value of what is it, the value of your speed. So another method that we can use, this is redated. Another method that we can use is to actually use that equation for non-conservative forces. So remember, you were introduced to this equation that said the work done by non-conservative forces is equals to the change in EK, which is our kinetic energy, plus the change in EP, which is our potential energy, right? Okay, cool. So how do we then use this equation to calculate that speed of our object at that it is moving at? Think about it. So the important thing to know is that what are non-conservative forces? We've already mentioned to you what they are in the last lesson, and we said they are forces that are dependent on the motion of your object. So in this case, our conservative forces would be tension as well as friction. So we have the work done by friction plus the work done by our tension, which is equals to a change in EK is nothing but a half mv. Let me just write everything down quickly. So the change in notes that a half mvf squared minus a half mvi squared. This is our initial, this is our final. So this is what we actually looking for. And then here for potential energy is mgh final height. So after that block is moved to that final height, as well as minus initial height. I'm not sure why I wrote HF there. MGHI, right? Okay. So we know what HI is. HI is 0 because it starts at the bottom. If you take the bottom as our frame of reference, HI is 0 meters. HF, we don't know. How do we then find it? And VI is 0 as 1 meters per second. VF, that's there what we are looking for, right? So this is an alternative way to find VF. So what do we do? So remember we were given this. So they say that the distance from here to here is 4 meters, and then we have this angle theta here, and you see that this is actually the height. So this is actually a right angle triangle. We can simply use our trigonometric identities, and you should know how to do this, where you'll find that the sine of 30 is equals to the opposite side, which is HF. I'm lying, so this is HF divided by the hypotenuse, which is 4 meters, and you'll find your h to actually be equals to, so the sine of 30 is 4, is 2, is a half, and then a half of 4 is nothing but 2 meters. So we already have what HF is. We can just substitute in everything. You should already see how this is actually going to work out. Let me just remove this. And then on this side, we will have the work done by friction. We calculated it to be a negative of 712.88. You can also calculate the work done by tension, and when we did those calculations previously, that work done by tension is going to be 2,800. So make sure you are able to get this value of 2,800. A half of mv f squared. Initial velocity is 0, so this thing is going to be 0. As well as on this side, initial height is 0, so this entire thing here, mghi is just going to be 0. So meaning you have plus mghf. And then now it's just a matter of substituting everything. If you do this thing, you get about 22812, and then let me just do this quickly. It's 70 kg vf squared plus 70 kg 9.8 as well as 2, which is our height. And then essentially if you solve this, you'll find that the value of VF is just going to be 2081.12 minus 70 multiplied by 9.8 multiplied by 2, all divided by 35. So this is just best. Make sure you are able to make VF a subject of the formula, and you're going to come to a value of about 4.52 meters per second. which is the same value that we found even previously. So yeah, so those are the three ways in which you can find that thing, and where you can apply the work done by non-conservative forces. You have to know what are conservative, what are non-conservative forces, or where you use the W net is equals to F net, a change in x cos of theta, and as well as where W net is equals to a change in kinetic energy. So make sure you are able to use all of these three formulas, and then you'll be ready to actually write that question paper. So the last question, which is question what is it? It's question 5.6, and it says that when the box is 4 meters up the incline, the rope accidentally breaks, causing the box to slide down to the bottom of the inclined plane. And what it says that what will the total work done by friction be when the box has moved up or down, up and then down to the bottom of the incline. So this is what they say. It moved up 4 meters and then it came back down. So remember, when it was moving up, we found the work done by friction to be negative 71. How much was that value? 712,88. Even when it's moved down, it will still be that work would still be about let's say down would still be negative 71288 joules. So it's just a matter of adding the two together, and then you'll find a value of about so that work done by the friction, which is the total, maybe write total there, would nothing would be just a negative of 142 comma 1425 comma 9 or 77, or you can say it's double the work. So remember that. So it's not gonna cancel each other. So because the value of it friction, because it always opposes motion, that value will always be a negative value. So yeah, this brings us to the end of this lesson. I know it's a bit longer than the others, but I just wanted to treat all of those different ways that you can actually find called use the work energy theorem, the work done by non-conservative forces, the network done when we have F net and everything. So yeah, I will see you guys in the next lesson where we're going to be talking about power.